let's think about what this first problem is asking, okay? We have a mass, we have an initial velocity, and we have a final velocity, and we have a time. Okay, so let's draw our free body diagram here, just kind of looking at what's going on here. Okay, so the system, here's our dot. We have a mass. We're going to have a braking force that's applied. Okay, and the braking force will be applied in which direction, the positive or the negative direction? Negative. Okay, so we're going to name that maybe just force brake, or F sub B. All right, does everyone see where that's coming from? Okay, are those the only forces that are on this bike right now? What else? The normal force and the gravitational force. So F sub G is the gravitational force. And how do we label the normal force? F sub N. And what is the normal force? Tell me what the normal force is and why we use it. It counteracts gravity, okay? The normal force occurs when an object is resting on top of another surface. Okay, so in this case, the bike's resting on the pavement or resting on the road, and we have to have that normal force pushing the bike back up. Okay, so anytime something is sitting on a surface, we have to count in that normal force. Is the bike moving up and down at all? Is it going up or down? No, it's not. So that means that gravity has to equal our normal force. The force of gravity equals our normal force here. We don't have any acceleration in the vertical direction at all, correct? No acceleration in the vertical direction. That means it's not moving up and down. So we have no vertical acceleration. That means our net force is only going to be in the horizontal direction. Does that make sense? When we work with net force, we have to work with horizontal or we work with vertical. Okay, so our net force here is only in the horizontal direction. So what net forces do we have, or what forces do we have to account for that are moving in the horizontal direction? Yeah, the braking force, F sub B. That's it, right? We don't have anything that's moving in the right direction, correct? Okay, and if we wanted to be really, really particular, we could have 0 minus F sub B to make it a negative, okay? And that's not something that I'm really particular about, but if you want to think in terms of right minus left, you could insert this 0 here. That's totally up to you. I'm okay with you just putting it and then giving a direction at the end, okay? So that's how I'm going to kind of keep it. So our only force here is our braking force, all right? So how do we find these things, right? How do we find this? We want to find how much braking force. We want to solve for this F sub B. Okay? What do we need to do? We need to find acceleration, correct? Because we can substitute our F net is mass times acceleration equals the braking force. Okay, does everyone see what I substituted right there? Force net equals mass times acceleration. Okay, so we need to find that. Let's solve for acceleration using one of our kinematics equations. Okay, we have velocity initial. And what's our velocity initial? Okay, good. What's our velocity final? 0, because it comes to a complete stop. Our time is 2 seconds. Okay, so VF equals VI plus A times T. So negative 5 equals 2A. So our acceleration equals negative 2.5 meters per second squared. Everyone see where we're getting that acceleration? Do you think that by yourself you would have been able to go this far? Okay, great. All right, so now we plug in our mass, which is 80, times our acceleration, which is negative 2.5, and we get what? Negative 200. And what's our units?
Newtons.
Good, newtons. Why do we know that our units have to be newtons?
It's asking for the force.
Exactly. It's asking for a force, okay? Whenever we're solving for a force, our units are newtons. What if it asks you for a horizontal acceleration, what's our units have to be? Meters per second squared. Horizontal acceleration, don't let that word throw you off. That just means that our direction is only going horizontal. We're not moving vertically at all. Okay, so we still use our net force that we find, all that kind of stuff. So if it asks for an acceleration, we find meters per second squared. If it asks for a force, you have to make sure it's in newtons. Okay, a couple of times on your homework, I've seen you mislabel the answers, okay? I want you to start looking back at what you're trying to solve for and know what unit goes with that, okay? Good. Okay, for this number 2, our free body diagram looks like force of gravity, which is pulling us down. And what's pushing up on us? Force of air resistance. Very good. Okay, so our net force will then be, if we follow our rule of up forces minus down forces, our net force will be what, Hunter? Tell me what the net force equation is.
F air minus FG.
F air minus FG. Very good. Okay. So we want to find the net force. We want to find this section of our equation here. We want to find our net force. What's given to us in the problem? What do we know? We know our mass right here. We know the force of our air resistance. We don't even have to do any math for that part. Okay, so F net equals our air resistance force, which is what? 150 minus what? How do we find F sub G? F sub G equals mass times gravity. So I'm going to take my mass here, which is 90. I'm going to take it times 9.8. So the net force then is what? It's what? Negative 732. That's what I got. Okay, if you take 150 minus 90 times 9.8. Okay, what would then be our units for this one? Newtons. Okay, because we're asked for a net force here. We're asked for a force. It has to be in newtons. Okay, this one you think you could have done by yourself? Confident? Okay, what is the skydiver's acceleration? Okay, is this one that would trip you up? Yes or no? Sometimes? Okay, so we have our net force right here. We just solved for it. This right here is our net force, 732. Here it is. Boom, negative 732. All we come down here and do is do our F net equals mass times acceleration. Okay, and we know that our F net equals negative 732. And we know our mass. And all we're going to do is solve for acceleration. Take our negative 732 divided by 90. And what do we get? Courtney, what did you get?
Negative 8.13.
Very good. And what's our acceleration units? Meters per second squared. Okay, does this number make sense? Does it make sense that it's negative? Why is it negative? They're falling downward. Okay, does it make sense that they're traveling less, or they're not accelerating as fast as gravity? Does that part make sense? Why? Because there's air resistance pushing up on them. Okay, so I want you to think big picture at your answers. If there's something pushing up on them, they shouldn't be accelerating at the speed of gravity, right? They're going to be slowing down. There's air resistance that's slowing them down. Okay? Feeling good? Okay. Let's move on to... Okay, so you have one ball that weighs 20 kilograms hanging above another one that weighs 10 kilograms hanging from a cable. Okay? And we're going to say that they accelerate upwards with, or at... let's say 3 meters per second squared. Okay, so they're accelerating upward at that rate. Okay, so we want to find the tension in each cable. We're going to solve for F sub t in each cable. So there's a cable right here and the cable that connects the two. Okay, so this would be F sub t, the force of tension in one, and the force of tension in the second one. So when we start to go about a problem like this, we have to draw our free body diagram for each of those cables, for each of those systems, okay? So we're going to look first at this F sub T1, and this is our free body diagram for that. We have the force of tension, F sub T1, that's pulling up, and what's pulling down? Yes, F sub G. Okay, so our net for this whole first cable, F net is going to equal up minus down, correct? We see that? Okay, F sub T1 minus F sub G, that's going to be our equation. So let's think about here, in this system on the top cable, what masses are we dealing with? Are we dealing only with the 20 kilogram, or are we dealing with 20 and 10? We're dealing with 20 and 10. So our mass of our whole system now becomes 30 kilograms. Okay, so for our net equation, since it's not at rest, since we know it has an acceleration, we cannot plug in F net equals 0. We know it's moving. We know the whole system overall is moving. So we have to plug in F net equals mass times acceleration. We do a substitution problem. We do a quick substitution here with F net equals mass times acceleration equals force of tension minus, what's F sub G equal? Mass times what?
Gravity.
Mass times gravity. Okay, so we just did a couple simple substitutions there. We talked about how since we're looking at our the top cable, the mass becomes what? 30 kilograms. What do we know our acceleration is for the whole system? 3. And is it accelerating upward or downward? Since it's accelerating upward, our acceleration stays positive. Okay, F sub T is what we're solving for, so we're just going to keep that in our equation, and we're going to subtract out 30, which is our mass, times 9.8, which is our gravity. Okay, so over here we have 90 equals F sub T1. What's 30 times 9.8? 294. Okay, so we add this 294 to the other side. We add the 294, and we get what? 384 equals F sub T1. Okay, and what's our units then? We're solving for the force of tension. Newtons. Okay, so that's the tension in our top cable. That's it. We just did it. Tension in the top cable. The trick for that is that you combine those two masses. Okay, that's the only thing that's different. We look at our net force, we know it's in motion, so we use our mass times the acceleration given to find that tension. Any questions on finding this first one? No? Yes or no? Okay. Can I erase this work yet or not quite? Okay. All right, now we're going to solve for the force of tension in this second cable. So we're solving for this right here. So our free body diagram will look essentially the same, correct? Except the force of tension pulling up will be F sub T2. And this is also gravity pulling down. Okay, so our net force equation looks the same, except we're dealing with our second tension force, so F sub T2 minus F sub G. We're going to do another substitution to have our mass times acceleration in there. We're solving for force of tension, so we keep that the same, and we know mass times gravity is also equal to F sub G. For this second cable, what will our mass be? 10. We're only looking at this bottom part right here. So the only thing pulling down on this second cable is this right here. All right. So we have 10 times the acceleration, which is 3. Our tension minus 10, which is times 9.8. Okay, so we have 30 equals F sub T2 minus 98. We add those over, and we get the tension in the second cable. 128 newtons. Okay, how's that feel? A little bit better?